Now, for demonstration of the tool, a floating wake plumbous P2 from the literature has been used. So this is the case study that will be released by the tool after an online training video that will be prepared. And the model will be uploaded along with the code to GitHub. This device is 750 kilowatt, but the power matrix that have been used for the case study is based on the contracted target power matrix during P2 testing, not a commercial rate. So meaning that the annual power production is much more less than can be expected for a commercial rate. And the site is in Far Point northeast of Scotland. So I go one by one through the different kind of tabs, which requires the different inputs for the model that has been developed. The project detail where we identify the number of iterations, lifetime of the project, and also other losses that will not be modeled explicitly in the model, like the wake loss, transmission loss, or any other losses can be entered as a percentage in the tool, and assume a grid rate, because the model will estimate the income over the lifetime of the project. And also the form detail. In the form detail, so we determine basically what technology type will be used. If it is wave or tidal, we can select here. And if it is floating or fixed. And one thing is that the user can upload their own power matrix or power curve for the analysis. And in the resources, again, the user can upload their own resource if they Metrosian data, I mean, which is quite user-friendly, and it could be, we believe it could be useful for the developers and the users to perform different kind of tests for the different projects that they wish. The next inputs into the model is the identify the base case. Base case is the port facilities which support the O&M operation. The model is limits to just define 3 ports in this tool. There are fixed costs for the O&M facilities and also technician costs. So these inputs are fixed, which will be identified by the users. And for the vessels, the model can, the user can identify up to 6, can input up to 6 vessels. And in the vessels, all the specification of the vessels, if it is purchased or if it is rented, so the user can select purchased. If it is purchased, then there would be annual fixed operating for the vessels. If it is rented, then the user can select if it is rented as required, or it is rented for a fixed period, or they can define the period. So a calendar will be pop up and the user can select for which period the vessel can be hired. The daily rental cost and mobilization cost and the mobilization time for the vessel can be input here. Fuel consumption of each of the vessels that users have added here, and the speed and fuel costs. So all these inputs are required for the model to calculate the vessel cost and the fuel cost. So as I said, this model also can somehow model the installation. The limit is only to installation of the device on and substructure can be modeled. If there are other installation, for instance, electrical infrastructure or other installation that cannot be modeled by the tool, then there is, so users usually input an estimated installation of all those other inputs here in the additional installation cost. Installation period has been defined, will be put by the inputs. It is important to for the user to give to anticipate enough time for the installation of their devices. It depends on the number of the devices and the type of the vessels that have been selected. And also the other cost component of installation, like project management and contingency and insurance, etc., can be added as a percentage of the total installation cost in this tab. Installation activities, so it's clear that should be installation time should be enough for the model to install the devices. In the next tab is the going to the maintenance strategy. So the tool can model up to 2 preventative maintenance or planned maintenance. For instance, for this case study, we have modeled 2 preventative maintenance, half-life refit, and regular annual refit. So the users can add tasks for this preventative maintenance. And here, again, if there is any other, because any other operation and maintenance costs with respect to preventative maintenance that have not been modeled, the user can add a fixed rate and estimate according to what they want here in this tab. Then the corrective maintenance have 2 parts. One is defining the repair categories. There is no limits for the repair categories. The users can identify, can define any repair categories like minor, major, intermediate, or others. And also they can define which port each of these repair categories will be will do the maintenance activity, and if it is onshore, if it is offshore, and also the weather window limits, which is and also the duration, operation duration. If it is onshore, then definitely the onshore and offshore will be pop up. If it is only offshore, then we have only offshore duration time. And the other limitation for this kind of activity, which is aligned with that particular repair category. And power loss, if it is 100% or not, and then the user can add other repair types when this one is finished. After completing the repair categories, we go to the components. So here, for this case study, there are 13 components that have been identified, and the input data have been inserted into the model. There is no limitations on the number of the components. But for each component, when we add the component, we define each component has this input data, the failure rate, the number of that component for that particular device, if it is tidal or wave, and the repair category, which has been defined in the previous tab. So each component is aligned or is associated with a predefined repair category. And of course, the spare part cost, the user can insert the spare part cost for each of these minor or major repair for each of the components. When all these inputs have been inserted into the model is ready the tool is ready to simulate, to start the simulation. First, the model simulates the installation. If the installation is successful, then the operation and maintenance will be simulated. Here is only one. We run the model only for one iteration, and the results can be exported as an Excel file as the yearly operation and maintenance breakdown results in these slides. And also the average of each of the iteration. So that would be an advantage, because for each iteration we have basically one rows of the average of the breakdown of the O&M cost, time-based availability, energy-based availability, theoretical energy, and energy which is produced. It means after reduction of the downtime, and all the detail of the vessel technician base cost, which is here in this model is fixed, and the total O&M cost. So when we have the different kind of iterations, we can analyze the data in more detail in terms of the standard deviation, in terms of the confidence interval calculations, and also the model produce the detail of the installation. There is one tab that produces when the installation has occurred and what time and how many attempts or trials have been done until the task is completed. So by having all this information, then we believe that this model can be used to create different scenarios. Basically, these are the work which now is in progress, and for this work there is some interactions with work package 4 and inputs from the industries that both industries have provided the inputs of their devices. We are just waiting for the updated power matrix of OE35 that in that case we can run some simulations, some scenarios. These are a tentative list of the scenarios that we want to run and to perform further optimization and sensitivity analysis. For instance, in terms of the vessel arrangement, in terms of the taking into account the weather limits, and if it is more optimal to use more expensive vessels, which has a better operational capability and learning. And in terms of changing of the failure rate by taking into account the technology matureness over the time, and also installation and operation duration, which is one of the main tasks, which provides somehow, which will be based on the learning rate as the economy of scale happened or experience increases with time. Work package 4 has so far has provided the method data for the 2 sites, Ireland and Wales, that will be used for each of these technology, one for wave, one for tidal, for the deliverable D83 and D84. And now the time series method data, only current data for tidal is in progress, that hopefully we will have it from work package 4. And also work package 8, when perform this scenario analysis and the sensitivity analysis to seek the optimal option, then can inform work package 4 about the most likely operation and maintenance costs that work package 4 can be used to conduct the full LCOE analysis, as Ross highlighted in one of the slides, for the interactions between work package 4 and work package 8. So that is the very brief overview of the model which has been developed.